Yesterday we started discussing caches. Motivated why we need a memory hierarchy and what is the main concept why caches really work in real systems because of locality concept. What we said is the 10-90 rule, right? So we said there are spatial locality and temporal locality. And we started looking into how do we compose this cache hierarchy into modern CPUs. Okay? We said the closest memory to the pipeline is in fact the register file. So the memory, we don't call it memory because, well, it's composed of multiple registers and people differentiate it from caches, but it's still a type of a memory, right? You store your values in those registers. Something that is very important to differentiate register file from cache hierarchy from main memory is that the register file is in fact accessible by the assembler, right? So it's part of that contract with the ISA. When you create like a program like C code, for example, and then you compile it into assembly, and you look into that assembly, you will find that there is an add R1, R2, R3, right? So the compiler is aware that those registers exist. If, for example, you have 32 general purpose registers from R1 to R32, you will not find that the compiler is generating an R100, right? So it's aware of those registers and is able to, well, use them. So the register or the register file is exposed to the compiler or to the software level. Why? Because it's part of the ISA contract, right? While we said yesterday that caches are purely hardware management, right? So they are they are completely transparent from the software perspective. The software doesn't need to know that what is the exact details of your cache hierarchy. Despite the fact that we said if you know and if you're a good professional programmer, you might be able to leverage some knowledge about the hardware to optimize your code. But for functionality perspective, it's not really needed, right? I can write my code. You guys have been writing code for many years without knowing what machine, like what is the exact cache hierarchy of the machines that you're using, right? And this is the good side of separating the concerns between the hardware and the software. So this is, if you look into the figure, it is why it's written that the register file is compiler managed. Here, well, the separation layer, whether which part is compiler managed versus not, is in fact going down to the caches. The caches themselves are not compiler managed. I1 and like the level 1 caches, or if you have multiple level 2. But then the caches themselves, L1, L2, or if you have other levels of caches, they are hardware managed, purely hardware managed. The main memory is also purely hardware managed. But there is a part from the main memory that deals with the disk, the virtual memory side. And I hope we would have the time at the end to discuss virtual memory. But at the very least, in your OS course, you might have already discussed how the OS, part of the OS management is the disk management, right? The file management. How can you really load programs from the disk, the main memory, and then start operating on them, right? So your ultimate infinite virtual memory is on the disk, and this is why it's operating system managed. The operating system does what is called paging, so it brings in pages to the main memory and operates on them. From main memory to the cache level, it's pure hardware managed. And if you go to the register file, well, this is compiler managed, which means the compiler is the one that is responsible for generating the instructions and what registers are being used. Good. So this is a very important differentiation to understand what happens under the hood and which memory level is being managed by whom. Good. And then we said that there is the ABC of cache organization, something called associativity, blocks, and conflicts. We discussed all of these. This is terminology that you need to understand. But final important concept we discussed is what does it mean to have a miss or a hit, right? We said a hit in a certain memory means you find your data in that memory. For example, if we say you hit in the L1, it means that the CPU issued a load instruction or a store instruction. It went to the level 1 cache and it found the data there. If you don't find your data because the cache is small sized, not all the data will be in the level 1 cache, we call this a miss. And what would happen when a miss? You need to go and bring the data from the lower level cache. You go and search for the L2, which is a bit bigger. And then if it's not in the L2, you go to that subsequent level, etc., until you find it. Good? Make sense? Great. So now we delve a little bit into how do we really organize a cache? How does a cache work? So then we give a very simple example, but this example is important to understand the general organization. So assume you have 1K entries, 1024 entries in a memory. So you're designing a memory right now. And it doesn't matter what level you're in. We're just talking about, I'm designing a cache memory. If I have 1024 locations, how many address bits I need? 10 bits, right? Because 1024 locations, 2 to the power 10. So you need 10 bits to address them. How much data entries you have versus how many addresses? This is something I would believe you have already went through multiple courses. In electronics that have been discussed, in embedded interfacing in second year that have been discussed, right? Simply look into how many entries you have. You see how many bits you need to input the address, and then this will compose your address bus. If you have 10-bit address bus, that means I have distinctive 2 to the power 10 combinations, which means I can address 2 to the power 10 memory locations, right? 1024 entries. But this is why we have 1024 data locations, and I have 10 address bits. If I want to get the total size of the memory, what would be the total size of the memory? With what I told you so far, in fact, you're not able to say. Because I told you the number of entries, but I didn't say one entry is composed of how many bytes, right? So you need to know the number of entries, but you also need to know the width of each entry, right? If you assume that each entry here, for example, is 256 bits, how many bytes is this? 256 is, that's 2 to the power 8, 3 to the power 5, that's 32 bytes, right? So if you assume every entry is 32 bytes, then right now you can compute the total size of your cache or your memory, right? Say I have 1K entries, every entry is 32 bytes. That means this memory is 32K bytes. Good. So this is the fundamentals of memory in general. You need to know how many address bits you need, what is the number of entries, and what is the width, how many bytes is in every entry. Good. Great. So in caches, we start, this is a general memory terminology. Again, if even you're designing a VGA or own SRAM, you need to know that stuff. In caches, we call these things with a certain terminology in a cache. For example, we call one entry a cache line. Good. So one entry in a cache is called the cache line, and this is the address that is being generated by the CPU to access the cache. Later on, we will see how we can really chop in that address width to determine which entry I should go to and which byte I'm looking for. Good. And this is what we're doing in this line. So assume you have an address of 32 bits from 0 to 32. And simply, if I'm telling you that there are, well, first of all, let's talk about the locations. We said there are 1024 locations, and I need 10 bits to address them. We call these 10 bits as part of the CPU address, the 32 bits of our CPU address. We call them the index because you use them to index your cache. Good. But as you can see right now, they are part of the address. It's not the whole address. Right? First of all, because we know that our machine we're considering is 32-bit machine, which all the registers are 32 bits, so your address will also be 32 bits. But also the CPU, your software does not generate addresses that only fits into L1, right? It in reality generate addresses that might fit into whatever memory space you support. So we said in one of the early lectures that one of the things that define your machine is the width of the machine. We call this the machine width. We call this is the register file width or the register width of your machine. For example, most of our laptops right now are 64 bits. A while ago, 10 years ago might be, we have 32-bit machines. Arduino is an 8-bit machine. When we say that stuff, what do we mean? We mean that the registers are in fact with that width. So now the CPU, when it generates an address, it generates an address that is 32 bits because it does not have, we said the software is not aware of caches. So it basically deals with the full memory address space. What is your full memory address space? I have 32-bit address. That means I can address 2 to the 32 locations. Where are these locations? In which cache level? Software does not care, pipeline does not care. When you issue the load instruction, you don't even know when to find it. Good. This is basically your full 32 bits. But when you go to access L1 first, you only have 1024 locations. You don't have 2 to the power 32 locations. You don't use the full address to access this cache. You use only part of it, and we call this part the index. The index is easily computed based on how many locations you have. Here there are 1024, so I need 10 bits. Why I didn't pick up the 10 bits to be from 0 to 9? I picked up, shifted like this. Can anyone guess? So someone can say, okay, if you need 10 bits out of the 30, then we take 0 to 9, right? Yeah. Yeah, thank you. So it's basically, 32 bytes, but, and this is the width of the entry, right? That's not the register, but more it's like the entry in the cache, right? But you're correct. The idea is that this index gives you an access to one of the locations, one of the entries. But we have a load byte instruction. We have a store byte instruction, right? Those instructions will be accessing, in general, a certain byte. They will be accessing the full entry, right? So in that case, after I go to a particular entry, I might need to pick certain bytes out of this entry. So we call this the offset of the address. Because once you go with the index to a certain location, if the CPU is requesting a certain byte or bytes, you use the offset to get those bytes. Here we had a 32 byte width of the entry. 32 bytes means how many bits to index them? If you are byte addressable, 5 bits, right? 32 to the power 5, so you need 5 bits. So why our offset here is 5 bits, 0 to 4, and our index is the next 10 bits. Good? So far, up until now, I went to a certain location and I picked certain bytes out of that location. So I'm done, right? What do I do with the rest of the address? Is there something missing with this argument right now? Is there something that we didn't discuss? So I went to a location and then I'm indexing a certain byte. Yeah. Exactly. There is the thank you. So there is the possibility that simply once you go there, you might not find it. You might find another cache line, right? Why? Because it's a many to one mapping, right? You have 32 bits, you have about 32 locations, but you only have 1K locations in this cache, which means one entry, in fact, might be holding multiple cache lines, right? Multiple memory locations. Which one is there? I don't know, right? What is the best way to know? Well, simply, since you have 32 locations, every 32-bit are unique. So in that case, you use the rest of the address, what we call a tag, to determine whether the cache line you found here or the entry you found here is the one that you're looking for or not. So now, let's go through the steps we have said again and see if that makes sense. We said, and by the way, the one that is doing all of this is called the cache controller. It's a logic and machinery that is in the cache that takes the address and does the following steps. First thing is extract the index, go to the location, so feed those bits to the address line, the memory gets you to that particular location. Before even checking which bytes you are looking for, you need to know whether the data in that location is the one they're looking for or not. The way to know this is you compare the tag, which means you need to store the tag here, as we'll see in a later slide. You compare the tag of that entry with the rest of the bits of the tag. If they match, that means this is the line I'm looking for. Then index the certain bytes you need and then get them. If they don't match, then this is a mess because something else exists in that entry and you need to go to the lower level of memory to bring that cache. Make sense? These are the steps you do to go to a particular location and check whether this is the data you are looking for or not. Good? Questions? Any question? So we see here from that image that because based on the line of thought we had so far, we needed to store the tag because otherwise I wouldn't know the data I'm looking for is the one that is stored or not. So I need to store the tag. This tag is the rest of the address, which means it's not a real data. It's something to check, right? So I add here what we call the tag array that is storing the rest of the address bits, which is here from bit 15 to 31. I go with the index, compare the tag, so you see there is a comparator. If it matches, then it's a hit, and then you go to index the particular line to bring in your data. If it misses, then it's a mess and you need to bring it from that lower level. Make sense? This is fundamental in caches. So if you have questions, feel free to ask because we're going to build on top of this the rest of the cache discussion. If there is anyone confused, feel free to ask. Okay, so now, given that this tag is not a real data, the entries here, it's basically an overhead. What do you mean by the word overhead? It means, in fact, it's not real data, right? It's something that is used to maintain the operation. but the real data that you're storing is here, what we call the data array. For that reason, people usually like to calculate the overhead of that tag array. It's called overhead again because it's something that is not real data, it's only needed for the operation. How to calculate the tag overhead? In that example we have. Yeah. Yeah, so the size of the okay, you are getting the ratio. Yeah, that's a good way of thinking about it. So you're getting that size, and then you divide it by the entry. So in that case, it tells you how much extra overhead you are suffering. But one step before this, if I want to calculate the total size of the tag overhead, not the ratio of the overhead, not a percentage, what I would do. Exactly. Size of the tag, which is basically the number of bits you store here. In our case, we have 32. We took out of them 5 and 10, 15. So I left by 17 bits. So my tag is 17 bits. And then I have 1024 entries. That means 1K basically, which means I have 17K bits as an overhead. Right? Yeah.
Like X equals 5. And then you try to use X later on. There's a tag that's created saying like this value is X.
That's okay. That's a good question. This is a good example, a good high-level example to walk through that, right? X equals 5 in your high-level C. What is going to be translated into assembly? X is a variable that generally might be stored in memory if it's not registered, right? So it will be a memory location. Then you say store in that memory location the value 5. This memory location, basically the way you go into it with an address, this address is 32 bits. And this is what we're talking about, right? So the tag is not associated with the data itself or the variable. It's basically part of the address of that memory location, which is this last portion of the address. Make sense? So in the high-level C, you have memory operations, for example, variable assignments, X equals 5, that gets translated into store instructions or load instructions. Those ones would have an address to go to the memory for particular data. This address by definition is 32 bits, similar to what we have seen earlier in the ISA lectures. Those 32 bits is what we're discussing right now, right? So this is coming out of the pipeline to the cache level with an address and the type of an operation. If it's a load, it's a read. If it's a store, it's a write, right? So the interface between the pipeline and the cache hierarchy is an address and a type, right? The address is simply the address, which is part of the instruction, and the type, whether it's read or write, based on whether it's a load or store. Yeah. Can you see that again? Yeah, in reality, if you think about it, well, first of all, yes, all these tags will be different. But in reality, by definition, by construction, they must be different because, well, no, they don't have to be different. That's correct. They don't have to. They are generally different, but the idea is the following. If the index of different entries means what from the address perspective? It means different index bits, correct? So those bits will change. Since you have 32 bits of an address, there is a possibility that one instruction, one load or restore operation, one memory request would have the same bits as this, but they will only vary here, right? Think, for example, about an array definition, an int of an array. And I have done this exercise with you in 2SH when we had the pointer stuff, right? If you define an array and you get the address of element 0 of the array, and then you get the address of the second element, third element, fourth element, you will find, in fact, they differ by an amount of 4 bytes, right? Because it's an int. 4 bytes means they will differ in bit number 0, 1, 2, right? The array, everything else will remain the same, which means the tag portion will remain the same. Well, in case of an int, the index is mostly remain the same because it's 4 bytes and your cache line is in fact 64 bytes. But if you jump by a stride more than 32 bytes in that example, they will start different in the index, but the tag will remain the same. Generally, any two different addresses, because the memory is byte addressable, any two different addresses must differ in at least 1 bit. Otherwise, they will be pointing to the same exact data in the memory from the pipeline perspective and from the software perspective, correct? This bit, 1 bit or more, doesn't really matter. This bit might be here, which means, in fact, in our cache, they will map to different entries. this bit might be here, which means I'm accessing different bytes on the same cache line. Or this bit might be here, which means they will be mapped to the same entry, but they are in reality different cache lines. They are different entries, correct? Different, like when you go to the memory, you are pointing to something else. Make sense? So the reason we're using the tag is this is a small memory, and my big memory, the one that is visible to the software and to the pipeline, is 2 to the power 32, which means it's a many to one mapping. One of those entries will possibly hold multiple entries from that memory. Which one do I have now is what's being determined by the tag. This makes sense? Another question? Yeah?
We count the validity overhead.
Yeah, that's an excellent question. Thank you. So right now, so far, I didn't say that, oh yeah, there is a valid bit, but I didn't discuss at all. So I told you that the process is I get the index, go there, compare the tag. If it matches, then it's a hit. But in reality, it might match. So the tag is the same tag, but the cache line is not valid. Not valid means it's a mess. It's not there. The data is not a valid data. So most caches hold in one extra bit that is called the valid bit. That tells you also it's not enough to have a match, but also whether the data there is valid or not. What might make the data not valid even if the tag is there? Multiple things. For example, maybe for example another processor, and you'll see this later on, another processor requested the same cache line, wrote into it, which means you have that data, but this is a stale data, old data. Right? And we have what we call a coherency issue that we'll discuss later on. Another possibility is you might have at the very beginning, the cache is holding garbage, right? At the very beginning, just completely any data. So the tag can be anything. But then you need at initialization to, in fact, reset all your valid bits, which means I start by saying I don't have anything in the cache. Even if there's any garbage, it doesn't mean it's valid data. So the valid bit is used to determine whether your data is valid or not. Consequently, if you want to hit into the cache, you need to achieve two conditions. Your tag matches and the valid bit is 1. Right? This is the reason why you are using the valid bit as well as the match of the tag. Okay. Other questions? There was another raised hand here. Okay. Yeah, this is the tag overhead calculation that we have already went through. So far we discussed what happens if you have a cache hit, right? You compare it matches the data. If it doesn't match, then I need to do more work, right? Because that particular cache, remember what we discussed yesterday, is that in that hierarchy here, if I try to access, for example, L1, L1, let's say L1 as an example, but I didn't find my data, the A0 example that we had yesterday, I will go and look into L2. If I find it in L2, I don't only send the data to the CPU, but what else do I do? To apply the locality concept for future accesses. I also bring this data into the L1. Right? Because I want later on, if I access it again, I find it in the L1. Not every time I need to go to L2. Right? So usually, as part of the cache operation to handle a mess, if there is a mess in that level, it goes to the lower level, in that case is the L2, ask them, do you have the data? If you have the data, please feed it to me, and then you also feed to the CPU. Why I bring it to the closer to the CPU? Because according to the locality concept, most likely I'm going to re-access that cache location again. I don't want to go to the L2 to get it, or to the main memory. I need to access from the L1, right? So upon a mess, you need to do some more operations. Because you are going to get this line, we call this a cache refill. You're going to get it from the lower level. When I receive the data, I need to match it with the previous request. So you need to hold that request waiting for you until the data comes from the lower level, because it takes some time. So you basically remember the miss address, you store it in a register. We call this a miss status register. And then you access the next level of memory to check whether the data is there. You wait for the response. Once the data comes in, well, you might be receiving multiple requests, right? You might have multiple requests from the CPU, all of them are misses, so you send all these misses to the lower levels. You might have multiple data coming in, so you need to match the data with the waiting address. And once it matches, you simply need to write the data and the tag into the proper location. in the cache level, and you need to send it to the CPU, right? Well, replacement policy is something we didn't discuss even yet. I'm assuming, but yeah, forget about this one now for a second. Just make sure you understand the process. So again, if I have a mess, what do? I store the request address. I keep it with me. Send the request, forward the request to the lower level caches. Wait for the response. When the data comes back, I match it with the address. Take them, write them on my own cache, hoping that in future accesses they will be heads. Make sense? Questions? Great. So far, we're also optimistic a little bit. We're assuming that when I receive the data from the lower level of the cache, I'm going to store it in that location and I'm done. What if you don't have place in your cache? What if every single entry in the location have valid data? That's a possibility. Again, because I have small cache and I need to map multiple entries to one place. Right? So what do I need to do? I need to evict one of the existing lines, remove them, and update the new line. Right? We call this a replacement policy. A replacement policy happens when you try to bring in a data from the lower level cache. When you try to write it, you find that your cache is already full, or that particular entry already has a valid line. In that case, you need to evict the old line and put the new one. Right? Yes. And we'll discuss replacement policy later on in more detail, but that's the general concept to understand the full story of what happens for a miss. Good. So now, again, attributing everything back to performance, we need to measure the performance. Why caches are good, why the performance is nice. Because if I want to calculate the average access time, the memory access time of a particular cache level, now we have different types of requests. I might have a hit. If I come to the cache, I might hit, or I might have a miss, right? And the hit, which one has a larger delay or larger latency? Which one do I prefer, the hit or the miss? The hit. Why that's the case? It takes less time, right? If you wait until your L1, it's way better than if it misses on the L1 and you need to go to the L2, right? Remember, the idea of the cache hierarchy is that the closer you are to the CPU, the smaller the cache, but the access time is way smaller. And I gave you numbers yesterday from most modern machines that L1 is 1 to 2 cycles access time, but L2 is in the range of 10 cycles, while main memory is 100 cycles, right? So you see that if I miss in one level, I need to pay the extra cost, what we call a miss penalty, to go to the subsequent level, right? So if I want to, some requests will be heads, some requests will be misses. Ideally, I want all requests to be heads. And in that case, my total memory time would be the number of hits, which is the number of accesses, multiplied by the hit access time of that cache, correct? But that's the ideal scenario. Worst case scenario is all requests are misses, and then I multiply them by the miss penalty. But the general approach is some of the requests are hits, some of them are misses. If I want to calculate the overall access time, the average access time, what I would do, they would say my average access time is simply the hit time. So maybe I should, from where did I get that equation? To assume you have 100 requests, assume 30 of them are hits and 70 are misses, okay? And assume that the hit access time is 1 cycle, while the miss access time is 100 cycles for now. Good. In that case, what would be the total memory access time? Yeah. 7,030, that's correct. So basically I have 7 requests, each one of them is suffering 100 cycle. I have 30 requests, every one of them is suffering 1 cycle. I have simply 7,030. This is my total access time. If I want to calculate the average, what does it mean to be an average? Average means one request takes how much time? So I would divide by 100, which is my total requests, correct? So the average access time in that case is 70.3 cycles, okay? In other words, it means in average, a request would take, oh, how it's 70.3? Is that correct? Did I do something wrong? So this is 7,000. This is 30 cycles, 130, and then I divide by 100. If you divide by 100, you get 70 plus, yeah, 70.3. Oh, but this can't be, because I cannot be larger. Oh yeah, because you have access time of 100 cycle. Okay. So you see that the average here, I was thinking that the average is 70 cycles. You see that the average request access length. So in average, or on average, one request is taking 70 cycles. Why? Because here we have a majority of misses, right? So simply you look into the latency line here. Many requests are taking 100 cycles. Some 30% of them are taking 1 cycle. Your average is something in between, 70.3, right? This equation is the one that is used to calculate that average. I'm just simply dividing this miss rate is simply the number of misses divided by 100. Because if you look into that equation here, and then I divide it by 100, what I have done in reality is I said, okay, I have the number of misses divided by the total number of requests multiplied by the miss penalty or the miss access time plus the number of hits divided. So the number of hits in that case is 30 divided by the total number of requests and then multiplied by 1, right? Make sense? So this is how I did calculate the average in reality. Okay? Makes sense? In that case, this equation generally, I can say I need also to multiply by the hit rate, right? What is a miss rate and what is a hit rate? What is this terminology? So this is what is being written in that slide. Simply, we say a memory access is a read or a write to the cache, right? From a pipeline perspective, which what we have learned so far, is in fact a load or store instruction. But once it leaves the pipeline and go to the cache hierarchy, we call it a memory access. Memory access can be either a read or write. A read in case of a load and write in case of a store. Hit and miss, we have already discussed. Fill, as I have said earlier, in case of a miss, I need to bring in the data from the lower level. We call this a cache fill or a cache refill because originally this cache line wasn't in that cache level and you went and you brought it from the lower level. Simply a fill is an action of placing a data into a cache. And then in that equation, we have what we call a miss rate and hit rate. So simply, the miss rate is the number of misses divided by the total accesses, and the hit rate is the number of hits multiplied by, divided by the accesses, right? Just a simple averaging mechanism. And then the T hit and the T miss. T hit is the time that is taken by an access if it hits into that cache level, right? For example, the hit latency of an L1 cache is 2 cycles or 1 cycle, right? The miss penalty is how much time you take, which is here called T miss. How much time do you take to bring in the data from the upper level? Okay. Make sense? Questions? This memory average time is a measure of how good is the memory. Ultimately, as I have said, if we design your cache to be hit as much as you can and you minimize the hit latency, and this is something maybe you should also discuss. As part of that equation, based on the metrics do I have, which terms do I want to increase and which terms do I want to decrease? What do you think? What is the best case? When I architect my cache, with the light, we said before, if you architect something, you provide an idea. At the end of the day, you want to improve the performance. If this equation is the measurement of your performance, what is your goal? What do you want to do? Let's take them one by one. First of all, T average. What do I want to do with the T average? Yeah, minimize it as much as I can. That's an access time, right? So this is latency. Remember in the performance lecture, we said we have throughput and latency, right? This is latency because this is measured in time, right? So I want to minimize this one. To be able to minimize this one, let's take them one by one. The T hit, the hit access time. Do I want to increase or decrease? Decrease, because you want your access time to that particular cache level, the hit, to be as low as possible. What about hit rate? You want to increase as much as you can, right? Because if you increase the hit rate, at the end of the day, the hit rate plus the miss rate is 1, right? So if you increase the hit rate, in other words, you are in fact decreasing the miss rate, right? So I want to increase the hit rate and decrease the miss rate. What about TMS penalty? I would also decrease, right? So ultimately from this equation, my target is to improve the hit rate and minimize all the time penalties, the hit access time and the miss access time. As you will see later on, almost all design ideas are trade-offs between these things. If you try to improve the hit rate, this will come at the expense of either increasing the hit time or the miss penalty. If you try to improve the miss penalty, this comes at the expense of increasing the miss rate or decreasing the hit rate or increasing the hit assist time. So there is always a balance between those, right? There is no one solution that in fact helps you minimize and optimize the terms that you need to at the same time, right? Which I guess is the nature of life all the time. Great. So here in that slide, there is a further discussion related to how we